Hi, I'm Vladimir Cardenas, and I'm here to present my Teach One for our final project data preparations using the All of Us Research Workbench in the course HAP823, Causal Analysis and Comparative Effectiveness, taught by Farrokh Alemi, PhD. Before we start with my Teach One, I would like to make sure that you have created and imported your datasets that we need from all of us. You have to have created your concept sets and datasets, imported them into a Python Jupyter notebook in all of us research workbench, and renamed the datasets into our standard, more easily understood variable names. The video instructions are available in the open online courses page for causal analysis and comparative effectiveness. Go through the All of Us project page and scroll down to section B, creating a cohort and related datasets. That is, go to openonlinecourses.com, go to causal analysis and comparative effectiveness, and then click on All of Us project. In this page, scroll down until section B, and our videos will be this one for my Teach One, and then other Teach Ones that are made by other students that are very, very helpful as well from Rasil and Mona. You can watch them. Make sure you have done them before you continue with this Teach One. Okay, now that you have done your data import, we will now prepare our datasets to make them ready for analysis. Okay, our first step is to group similar antidepressants together. We will also fill out the dates and dosages for each antidepressant trial of the persons we are processing in our cohort. We will process the data to create the outcome variable that we want to measure, which is remission. We will also create variables for age groups and gender, or being female. We will process the disease dataset and create dummy variables for each of the diseases present prior to the antidepressant trial. And finally, we will create an analysis dataset for each antidepressant group that we are interested in studying. Okay, to start our analysis, we have to log in to All of Us Research Workbench, select your workspace, go to the Analysis tab, and then find the code where you imported, or the notebook where you imported your files or your datasets. For me, it will be the HAP823 Spring 2024 final project. Okay. Before you click on this link, I want to tell you that some of these codes will be very, very large, meaning it will process a very large data set. Okay, millions of rows, thousands of columns, and it will cause you to need a bigger server. You will know that you need a bigger server because your kernel will die. There will be an error that kernel is dead. Okay? When you run into that, you will go to this icon on the right, Jupyter Cloud Environment. Okay? Click that, and you will now be able to change your server size. Okay? For my own project doing this, I just selected the biggest one. Okay, I just selected 96 CPUs, 624 gigs of RAM. It will cost you $5.69 per hour, but at least it won't prevent you from like redoing your analysis over and over again when the kernel dies. Okay, this code that I will show you will allow us to save the data sets that we have processed after the analysis. As such, we will not need this big server every time. We will just need this big server for the initial run, and then we can go back to the small servers. For the small server, I do not recommend the smallest one. I would recommend the 8 CPU server with a 30 gig of RAM. Okay. So again, once you selected your server, so I will, for example, select the biggest server here. Okay. I would also recommend that you change this automatically pause instead of 30 minutes, make it 8 hours so that your server will not pause after 30 minutes. Leave the other things like the disk type by default and then click on next. Like when you click on next, it will confirm that you want to change your server and you can do that. I won't do that for this session because I already done that and my credits are running low. But you might have your full $300 credit, so that's fine. Okay, so I will just stay with my 40 cents an hour um, server. Okay, so click on your notebook. Okay, again, make sure you have a big server ready and then click on edit. Sometimes it will take time for that to load, but I have done this. I have loaded the files before this session, so it took a very quick time, but just be patient. Okay. So here, this is the code that we have imported. Remember, so just run every cell. Okay, and then this is the code where we have renamed our datasets into more standard, easily understood datasets. Okay, just run them. And then the code that I will present will start at section 1.3, data preparation. Okay, so let me scroll down and I will just zoom it in a bit so that it can be easily seen in the video. Okay. The first thing that we need to do is to group the antidepressants together. Okay, I will skip over the code and then show you that there are each antidepressant coded in all of us are different based on not only the active ingredient but also the dosage and the method of application, like a capsule, a solution. Okay, so you can see here at the bottom, doxypan has 10 milligram oral capsule. It's different from doxypan 10 milligram oral capsule and then with a sign something. It's different from an oral solution, right? So there are different types of doxypan. We wanted to just group them as doxypan, okay? Because we are interested in the impact of doxypan, okay, and not of the individual um, formulations of doxypan, okay. So to do that, I have created a grouping file that's available as well in the All of Us project page in Open Online Courses. I will show you where that is. So again, in section B, cohort and related datasets, there will be organizing antidepressant CSV. Download that onto your computer, okay? And then in All of Us, click on File, click on Open, and that will get you into the data storage of All of Us for your workspace. Okay, so these are all the data available in your workspace. Okay, you can create a folder to folders actually to um, organize your content. Okay, I created a data folder to just put in all the data sets that I have imported into all of us um, in a more organized way. But you can just put it on the root folder. That's okay, right? You can rename your folder whatever you like. I created it as data. So how do you create a folder? You click on um, this button here, new, and then click on folder. It will create an untitled folder for you. Select that and then click rename. So I'll sample, um, create a sample folder here. Okay. And when you go to sample, you have that folder. Okay. So I created a data folder. I go to data. Okay. And then I needed to upload this file, unique AD group CSV. Okay. I will just delete it to demonstrate this to you. So I will click upload, click OK in this affirmation that you will not upload data with personally identifiable information. Make sure that and this is not a data with personally identifiable information. It's just grouping antidepressants together. So click OK. Okay, it should pop up. Okay, click OK, and it should pop up this um, file explorer, and then I find the file that I have just downloaded, the grouping file that I have just downloaded from my computer in my computer, and then select that and click open, and then finally click upload, and you will have uploaded that file. Okay. Once we have uploaded that file, we can access it very easily. Read it using our pandas CSV read method. Okay, I read that. I again included that in the data folder. If you didn't create your own folder, it would just be like this, right? You just put it in the base, the root directory. If your folder is something different, like for example, I put it in a sample folder. You can put it as sample, but me, it's just data. Okay, read it and then look at how the head is. Like this concept code stands for doxepin hydrochloride 10 milligram oral capsule, and I manually grouped it into doxepin. Okay, so now we can use that grouping file to group our antidepressants together. So first, you need to make sure the standard concept code of our antidepressant data frame is in the integer 64 format or the nullable int format, um, just to make sure that we can join the tables together because uh, one is in int and the other one is a string. Okay? And then we just use left join. We left join based on the standard code, and then get the AD grouping. Okay, and we have this. Each antidepressant is now grouped. Now that we have grouped antidepressants together, our next step will just be to check, right, roughly check how many participants we have. Just for descriptive statistics, we have 7,081 persons taking antidepressants from our cohort out of 9,000. Okay, and then we drop the columns that we will no longer need. Moving forward, we will no longer need uh, specific medication codes and specific medication names. We will just use their group antidepressant uh, value. Okay, so that's it for step one. Step one for grouping antidepressants together. Our next step is now to fill out antidepressant dates for each trial. Okay, we need the start of a trial, the end of a trial, how many days of dosage do we have for each trial. Okay, and we define a trial as um, a range of days where there is no gap between dosages that is more than 4 weeks. So if the gap is less than 4 weeks, it's just a random non-adherence. But if the gap is for more than 4 weeks, then we will assume that another trial started. Okay. So in this processing, we will limit to the first three trials. Okay. Uh, but yeah, some people might have more than three trials of antidepressants. We will just be interested in the first three trials for each antidepressant. Now, the antidepressant data set is so big, and we wanted to like reduce the dimensionality a bit. So we remove duplicates. Okay, is this just like before we remove the duplicates? There's 213,000 rows. After removing duplicates, we only have 178,000 rows. Okay, so duplicates are those that have the same person ID, drug start time and start date, the same AD grouping, and the same drug day supply. Okay, if these are the same, it's the same data. It's just duplicate. Okay, and after removing duplicates, we just look at the head of it just to inspect roughly exploratory data analysis. Okay, now we start processing the data set and put in the dates. The library that we need is the datetime library, particularly the date time method and the time delta methods. Okay, those two methods. We create a new data frame, a new empty data frame. We call it 80 dates data frame, 80 dates DF. Okay, and the columns will be person ID, the antidepressant you're taking or AD grouping, right? What trial number this is, okay? And these three will be the combination of these three will be our primary key for this table. And then for each trial, what's the earliest antidepressant start and what's the earliest antidepressant end? And then how many days of antidepressants dosage did you get? Okay. Now you see that when we initialize this data frame, everything was um, had a data type of object or string. We needed to change them to their proper data types so we can process them correctly. Person ID, trial number, and dosage days will be nullable ints. The start date and end date will be date time. Okay, and then we check if we have the right um, data types, and we have, so we can continue with our analysis. I also use info to double check, but yeah, that's just me being thorough, I think. Okay, so now we create a function to calculate the dosage days. But before I describe the function, I want to scroll down and see, scroll to see that we have a drug exposure start time and a drug exposure date time and a day supply. Okay, we have these data. Okay, and we can see that sometimes day supply does not have a value. It's not apparent here, but sometimes date drug end time has no value. It's also empty. But start time always has a value. So when you do exploratory data analysis, that's what you will find out. I wanted to describe that because that's where the design of this function comes from. So for each row, for each row in our data frame, we will have to check whether um, whether the end date is empty, the dosage date is empty, both of them are empty, or both of them have values, um, and make the appropriate data um, data decisions based on that. Okay. So the first scenario that calculate dosage days um, is will look into is when both the end date and the day supply do not have values. So if that happens, then we assume that it's a one-off single dose, one-time dose event. Okay, so that means the end date is the same day as when it started. Okay, so we put a value to the end date as the same day that it started, and then the dosage days is just one day. You just had a dose for that particular day. Okay, if the end date has a value, but the day supply has a value, does not have a value, rather, the end date has a value, but the day supply does not have a value, we will assume that you had enough dosages to until your dosage end date ended, right? So if the end date is 5 days from now, we will assume that you had 5 days of dosage. Okay, so we will take whatever end time we have, okay, and we will calculate the number of dosage days from the start date until um, until the current end date. Okay. Now, if the end date has no value and the day supplies has a value, then it's a reverse. We will now calculate the end date, and the end date will be the start date plus the number of days supply. The assumption is still that you have enough days, you have enough dosages until the end of that trial. Okay, so the trial end will be the start time plus the dosage days. Okay, and then the dosage days we will just take it as is. And finally, if both the end date and the dosage days have value, then we will just take their values. Okay, and then return the values of the end date and the value of the trial dosage. Okay, once we can calculate dosage days, we now process each person's antidepressant trials. Okay, so for each person, we will loop through uh, all the antidepressants that they're taking. Okay, so that's this loop. Okay, and then I have, for example, a person with 5 antidepressants. Okay, I will create for each of that antidepressants. I will create a loop run, a loop pass. Okay, so the first thing that I will do is I will create a subset for that person for that particular antidepressant. I will create a smaller data frame. Okay, and then I will just get the earliest time that they started that antidepressant. Okay, that will be trial number one. That will be trial number one. Okay, and then to get the next trials, I will sort the values based on start time. Okay, I will sort the values based on start time, and now I will have to track the end dates and the dosage days. Okay, and if the end date or the dosage days, if the end date and the next start date are more than 4 weeks apart, or if it's the last row of the process tracker, then um, I have to like append a new entry on our table. Okay, on our table of trials. Okay? A trial has ended. Okay, it means that the trial has ended, and then move on to the next trial. Okay, and if it's the last row or if it's the third trial, then I just end the loop because we only will track up to 3 trials. And of course, if it's the last row, then just end the loop there. But if it's not the last row, then we continue. We now track the start dates and the end dates of the next trial. Okay, of the next trial, trial number 2 or trial number three. And then I also track whether um, there's a there's a trial, there's a date in that in the data frame that is like within the trial that we are already processing, and I just skipped it. Okay. And then finally, if everything passes the test, then I will calculate the end date and the dosage days. Okay. And return all of the trials that that person has. Okay. So that's the function for process person. Okay. Now we will process um, we will do this process for each person. So there will be a loop for each person in our data frame. So, and now um, we will create a subset of the data frame for that person and then pass it on to process person. And then get the dates list or all the antidepressant trials that they have, and then append that into our data frame. Okay. Our final data frame will look like this. Okay. Again, person ID, um, grouping what antidepressant that they are taking, the trial number, the start and end date of that trial number, and the number of dosage days that they have. So, for example, this particular person, 3521063, has taken 3 trials of venlafaxine on these dates and with these dosage days. Okay. Okay, now that we have processed these dosage days, we will now be able to calculate whether they had a um, successful antidepressant trial or not. A successful antidepressant trial means that you had remission. Okay. So how do we define remission? So remission is when the trial is more than 70 days or 10 weeks, okay, and they did not start another antidepressant within that 10 days or 10 or within those 70 days or 10 weeks. Okay. So again, if the trial is more than 70 days and there are no other antidepressants started within that trial, then there's remission. There's a success in that antidepressant trial. Otherwise, there is no remission. The antidepressant trial is not a success. The first thing we will do is we will create another column called dose 70p, p meaning plus, 70 plus. Right? If there are more than 70 days of dosage, you will use NP where dosage days is greater than or equal to 70, then we set it to 1, otherwise it's 0. And then we will see if it's created correctly. Here it's 60, so there's not more than 70. Here is 170, so it is more than 70, so it's 1. Okay, so it worked well. Okay, now you want to track whether other antidepressants were started within the trial period. Okay, so to do that, we have to create a function to compute this, whether an antidepressant was started um, within the trial. Okay, so if an antidepressant was started within a trial, this function will return 1. Otherwise, this function will return 0. The first line is a heuristic. If there's only one row for that person, then they didn't start any antidepressant, right? There's just one trial for that person, just return the zero. So it will just make our code faster. It's an optimization run. It's an optimization code, right? But we don't need it. The other lines of code will run even without that, but it helps me make sure that things run fast. Having those heuristic events and coding that in. Okay. So now we will check whether 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 a trial is started within the 10 weeks or within 10 weeks of the antidepressant start. So how do we do that? Okay, so first we will track the start time of the trial, and then we will set the end time of the trial to 70 days after the start date. Okay, and then we will filter the rows for other antidepressants, meaning only for rows where the antidepressant is not equal to the current antidepressant. The row is the current, okay, the current antidepressant that we are processing. So that is what we call other rows. Okay, so those are rows for the same person ID, but not for the same antidepressant. Okay, and then we will loop through all of those other rows and find if there is an antidepressant that was started, right, that was started after the trial start, but before 70 days. If that happens, we return one. If the loop ends, ends, then that means there's nothing, so we just return a zero. Okay. And so to fill out other AD, to fill out that other, is there an other antidepressant that was started? We will create a column called other AD. Again, it will be one if there was an antidepressant started within 70 days. It will be zero if there was none. Okay. Now, again, for heuristics, we created a series that will just have the number of rows for each person. And then we will call the compute other AD function that we have just created and apply it for each row of our AD dates data frame, of our antidepressant dates data frame. And now we have um, the other AD column. Okay. And finally, for this particular portion of our code, we will create a remission column, and it will be one when those 70p is one, meaning there's more than 70 days of doses, but there are no antidepressant started within that 70 days, so other AD is zero. Okay, and then we created this column, and we can see that 0 0 is 0, right? And then there's 170 where those 70 is p is 1, and then other 80 is 0, so remission became 1. So now we have processed our outcome variable. We had created our outcome variable. We can now move on to our other task in preparing these data sets. In these data sets, so we will now create indicators for gender and age. Okay. First thing I did was um, created an analysis data frame. So an analysis data frame is just combining AD dates data frame, the dates data frame, with the demographics data frame um, that we have created, merging them together using left join on person ID. So that means for this data frame, I will need to get the birth date, the race, etc., all the other demographic details that we downloaded or we imported for each row. Okay. And then I also imported the date of death. Okay. So to do that, I renamed from the data frame, from the dead data frame I rename observation date time to date of death just to easily identify it. Okay, and then again left joined it to our analysis data frame. And that by doing that, this is our 80 dates data frame. It ended with remission as with our previous um, analysis, right? And now it added on other columns, okay, including date of death, okay, sex at birth, and ethnicity, date of birth, gender. Okay. Okay. I also did an analysis, an info of that analysis data frame, so that I can check the relevant um, data types and whether they are the right data types, so that um, I can pursue further analysis. And what I found out here is that the dates are strings and not dates. So I changed that again here to make sure that they're dates. So I made them to date time and then check the data types, and yeah, they're already date times. Okay, so now we can calculate the age because we cannot calculate an age from a string. We need the dates to calculate the age. So we create another column called age at AD or age at antidepressant, which is the age that the person is when they started the antidepressant trial. So it will just be the earliest AD start minus the date of birth, okay, divided by 365.5. So that's age in years. Okay. And then for date of death, there's a specific uh, qualification that we did that we only calculated age of death if the date of death is not empty. Okay. And that provided us with the age at AD and age at death columns. And then, since there are not a lot of persons who are dead, not enough, um, like less than 30 people who are dead, not enough for us to create uh, meaningful past relationships using uh, regressions. So we will just continue processing on agent antidepressant, okay? Because all of the 7,000 rows has an age of antidepressants. And we will use these age groups 0 to 12, 13 to 19, 20 to 20, 40, 41 to 64, 65 to 79, and 80 to 89. These are the age groups used in another study conducted by Dr. Alemi and his team. Okay? So we will just replicate the groups that they used. Um, just to make sure that there are no outliers, um, I looked at the minimum and maximum age, and yeah, and they fit these age groups well. Okay, so I will first define age groups, right? By creating them into creating bins and labeling those bins. So 0 to 12, age 13 to 19, 20, and use the cut method in pandas to create our age range column. Okay. And then from age range, I will create dummy variables for each age range value. So there will be a column for 0 to 12, 13 to 19, 20 to 40, and so on. And then add those dummy variables back into our analysis data frame. When we call head, we will have these new columns, age range, okay, and then dummy variables for each age range. Okay, and it will be 1 if that age range is a match. It will be 0 if that age range is not a match. Okay? So here, almost all of our first participants, first data are 41 to 64, but there is one who is 20 to 40. So There's one, the one is enabled or set for the appropriate dummy variable. Next, we will create an indicator for gender, again based on just replicating um, the the standard set by another uh, study conducted by Dr. Alemi's team. We will use female as an indicator, and that means so we will check gender, and if it's equal to female, we will just um, tag it as one. Otherwise, we'll tag it as 0. Okay. So here, all the participants in our the first 5 rows of our data frame are females. Okay. And now we will proceed with the next step, which is processing the disease data frame. If the antidepressant data frame was huge, the disease data frame is even bigger. It had for our cohort 4.7 million rows. Okay, so the first step that I always do is reduce dimensionality to make sure that I can process data more efficiently. So I remove duplicates, and by doing that, I remove almost a million rows. Okay, and duplicates are the same person ID, the same disease, and the same start time and end time. Okay, and though um, we have this format for our disease data frame that we have um, retrieved from all of us. Now I want to merge back diseases to our analysis data frame. Okay, so um, by left joining it, and we have our initial analysis data frame. Again, it ended at female, right? And now we have additional columns for standard concept name, standard concept code, condition start time, condition end time. Why do I need to do this? Because I want to further reduce the dimensionality, right? So now we have 18 million rows, right? Because for each trial, there are uh, mil- thousands, if not millions, of diseases for each trial, right? Or thousands of diseases for each trial. So what we want to do is remove any condition that started after the antidepressant trial. We are only interested in conditions or diseases that happened before the antidepressant trial started. So from 18 million rows, by doing that, we remove anything that started after the antidepressant trial. We ended up with now 6.6 million. And this is how that cleaned up data set looks like. Okay? Now, we will proceed with the final step that we will go through for this data preparation, which is creating analysis data frames for each of the antidepressants we want to study. The first thing I will do is to preserve whatever we have done earlier. So by this time, we have had run more than 40 sections of code. Okay, and we don't want to run them again and again and again every time we come back to all of us. So I create a data checkpoint so that we can store the state of our data and then access it from a file later on. Okay. The first thing that I'm doing in creating a checkpoint is to run an info so that I know the data types of each row of each column rather of the data types of each column before I saved it into a text CSV file. And So later on, when I read the CSV file, I can make sure that the data types are still the same. Okay. And then once I did the info, I wrote that down into another file, a CSV file. Okay. So if you click open here, you can either follow me with where I created another folder called checkpoint. Checkpoint is a folder for organizational purposes that I use to put in data checkpoints or data sets that I saved for later runs, just for organizational purposes. Okay, so I created that. So if you do that, you will use this code to write to a CSV file. But for me, but if you did create a folder, your code might be like this. If you create a different folder, like for example, um, another folder, right? Another folder, then your code will be that other folder name. Mine is checkpoint. Okay, so that will say the state of my analysis data frame. Okay? That means succeeding runs. I don't have to run the 44 lines of code, 44 cells of code that I have initially created. I can start at cell 45. Okay, and then I'll just import the relevant libraries like pandas, numpy, and os. Okay, and then I can read the checkpoint file that I created by using this code. Okay? Read CSV. I use low memory because this file is huge. We want to prevent low memory warnings. Okay, and then I did an info again. Check if the data types are still the same. Okay, and I found out that those that need to be integers are still integers, floats are still floats. Okay, but the dates were not coded correctly after import reading the CSV file. So these are all the dates columns of that checkpoint file, and I changed them into date time. Okay? And then I also use this opportunity to rename standard concept name into a more understandable name. I called it disease name, and then standard concept code into disease code. After that, when you run info, you will see that the dates are now coded as dates properly, and then disease name and disease code are again renamed. Okay, and our analysis data frame looks like this. Okay, this file is huge. Okay, I'll go back to our info file. It's 1.5 gigabytes, more than 1.5 gigabytes of memory is being used. Okay, so we need to reduce the dimensionality, or else even if we chose the biggest server, it will still kill our kernel. Okay, it will still not run. Even at 96 CPUs and 600 gigs of RAM, what we are trying to do now is create disease dummy variables. And there are thousands of disease available, right? And we will create one column for each of those unique diseases. So the first thing that we do to reduce the dimensionality of our data is just keep the data that we need, drop everything else, drop everything else. So this should be 0 2. Drop everything else, and if we need them later on, then we just add them in. Okay, so that's our strategy. So the columns we will keep will be person ID, the antidepressant grouping, the trial number, our primary keys, if you still remember, these are our primary keys. The earliest start of that antidepressant, because we will use this still to probably filter out um, unneeded data later on. Okay, but we can drop them. We can drop it later. Okay. Our outcome variable, remission, our age groups, our gender, and of course the disease code, because we will need the disease code to create the dummy variables. So when you do that from 1.5 gigabytes, it's now just 611 MB, right? Less than half the size. Okay. The next thing is I wanted to make sure that there is no empty disease code value, or else we have to do additional processing to make a dummy variable for that. Um, Fortunately, there is now no missing value. Okay, but if there is a missing value, then we have to put a default disease code. I think for purposes of uniformity, the default disease code will be 0. Okay, so that there are no um, missing values for the disease code column. Okay, so for our next step, which is like what I did, but the design idea here is that I will create um, a mini analysis file for each antidepressant. Okay, so that we can significantly reduce the dimensionality of the data. Okay, so I will loop through each of the unique antidepressants in the file that we have in the big analysis data frame that we have. Okay, and then create a subset for that antidepressant. Okay, and then create a disease per trial data frame that we will use as a base for our dummy variables. Okay, for our dummy variable creations, and then just create the dummy variables from the disease per trial data frame, and put the dummy variables back in disease per trial. Now that we have the dummy variables, we can drop the original disease code columns from both the disease per trial data frame and the analysis data frame, the subset of the analysis data frame that we have. Okay, and then because we will be trying to model regressions on this, we will drop any column column, meaning a column that starts with disease. So remember when we created our dummy variables, we have a prefix disease. That will mean everything will start with disease underscore. All the dummy variables will start with disease underscore. So if it's a dummy variable, but the sum of the column is less than 30, meaning there are less than 30 samples of that disease, we'll just drop that disease. And that will allow us to have a smaller data set that we can more easily process with regressions. Okay? Chain of regressions. Okay, and then we drop all of those columns. Okay, with less than 30 samples, and then we now combine that back to our analysis data frame. Okay, so but before that, we aggregate the values first. So for our analysis subset, we will use the first value of any column that is not the primary key. Okay? And then group them by. So it's similar to SQL group by. So we will group by person ID, AD grouping, and trial number, and we will use the first value of that column that we will group by. For disease, for the disease dummy variables, we will use max. We will use the maximum, meaning if you had that disease for that trial, then it will be 1. We will get the maximum. Okay. If you had that disease, that means you had that disease prior to the trial. Okay. We will aggregate using max. And once we aggregated the analysis subset and the disease per trial, that's when we left join them together. And then we create a checkpoint file with for each of these data frames. Okay. And then write them into a CSV file. Okay. So now what will that will result into this. So again, I created a checkpoint folder for all of my checkpoints. You can choose other folders or you can just use the root folder, but I use the checkpoint folder. So that means we now have an analysis data frame for amitriptyline, for bupropion, for citalopram, and then the flaxine and everything else, and even for other antidepressants in our grouping. Okay. And lastly, this is a code so that we can read the files later on in a more systematic way. Because we wrote them down in a checkpoint, we can now just, again, instead of running 50 code sets, we can start from from cell 54 and just start importing the libraries and reading the files into a dictionary. Okay? So how do you access the dictionary? I created a dictionary here. You can access it by analysis, dictionary, and the antidepressant, and that will give you the entire data frame for that antidepressant, which we can use for our later analysis for uh, for regressions or and population statistics. Okay, so this is the code again. Import the libraries, and then I listed down all of the antidepressants that we have a file for. Okay, and then initialize the dictionary, and then wrote each data frame into that dictionary. And this is how we will access it later. Okay? And I'm able to like make sure that I'm just making sure that I can read each of those data frames. Okay. And that's it. Thank you for listening. And if you have any questions, don't feel free to contact me during class. And yeah, good luck.